So hello everyone and welcome to this next lecture on the DC to DC converter series. So in the previous lecture I had completed the buck converter simulation. So this was pretty much where I had left off, and this was the buck converter circuit. So just to wind up, I had actually simulated most of them, analyzed the waveforms. So in this lecture we will start with the next converter, which is the boost converter. So before I start with this lecture, as before, just a quick info that if you are interested in this kind of video lectures but you find these video lectures too brief and you want something more comprehensive, I do have an full-length online course on how to simulate power electronic circuits using Python, where I go through the entire process of how to install, a little bit of basic theory of power electronics, and also a more detailed simulation of a buck converter. So this is in case you are interested in this but you find these video lectures to be a little too light and you want something a little more heavy. This might be a good option. So now to get started with the next simulation, what we're going to do is just go back to the simulation library, and we have this one simulation, which is the buck converter. So let's create a new simulation and let's call this boost converter. And of course you're welcome to give any description you want. I'll just give it the same name, no need to really go that far in this video, and the rest is pretty standard. Only thing, I'll just change the data step of time storage to be the same as the integrations time step. I'll let that be 1 microsecond. The circuit output file can be the same, and now the remaining directories. Now before I start entering this, let me go over to my circuit. This is the buck converter circuit. Now let me use this one to create a new simulation of a boost converter. So first and foremost, let me go over to my file browser. This is the directory where I have my buck converter simulation files. So let's go over to the parent directory and let's create a new folder. Let's call this boost converter. So this is the directory. Now I'm going to save this file as a new simulation in this new directory called boost converter. So I'm going to rename this as boost converter. Make sure that the format is still CSV and save it. And it will ask me this question, that because I'm not saving it in the default format, that's not a problem. So now I have my new file. Now the question is the buck converter. The buck converter, the reason why it's called a buck converter is because when this switch is turned on, right, this is the input voltage source, this is the output. When the switch is turned on, the input energizes the inductor and also the capacitor. And when the switch is turned off, the inductor freewheels through the capacitor. But it is important to note that when the voltage, the input voltage is connected to the output, it is charging both the inductor and the capacitor. So therefore the energy of the input is being split into two parts. The result is the output energy is always going to be less than the input energy. This is the reason why the output voltage is lower than the input voltage, and so it becomes a buck converter, right? You're stepping down the voltage. Now in a boost converter, things will change, right? So the way it works is this: there is a slight rearrangement in these components. So the way it works is simple. We now need to charge the inductor and have both the source, the voltage source, and the inductor charging the output. So for that we need to rearrange these components. Let me cut out these components a little, and let's remove the diode. Now the inductor comes in the position of the switch. So let me just cut out these components and put it here. So let me delete this first. And the switch now comes in the position of where the diode was before. And the diode now takes the position of the inductor. And I'll fill this up. So now let's look at what's going on here. Before, as I said, when the switch is turned on, I'll just save this. When the switch was turned on, the voltage source was feeding the inductor and the output voltage. That's when the previous path. Now, when the switch is turned on, the voltage source will charge the inductor, but it will charge the inductor through the switch, because remember, once the switch is turned on, this is the low resistance path. And when there is a low resistance path, the current will always choose the path of least resistance, which means this closed path will be the path through which the current circulates and charges this inductor. Right? This is when the current through the inductor charges up. Now, when the switch is turned off, the energy in the inductor has to freewheel somewhere. And that now freewheels through this diode to the output. Now, how is it different from the buck converter? When this inductor is discharging, there are now two sources that are feeding the output. It is the input voltage and the energy in the inductor. Both of them are now feeding the output. The result is the output voltage is going to be higher than the input voltage. We are now boosting up the output voltage above the input voltage. This now becomes a boost converter. So this is the concept of how you would build a boost converter with respect. This is how a boost converter differs from a buck converter. This placement of the components. All you have to do is visualize how the energy flows with respect to a buck converter and a boost converter. In one case, the input is charging both of them, that is the inductor and the output capacitor. Now the input charges only the inductor at one point of time, and at the other point of time both the input and the inductor charge the output voltage, and that is the reason why the output voltage attains a higher level than the input voltage. It becomes a boost converter. So let's go and add this. So I'll go back to my simulation. Well, actually I have to go back to my file browser, click on the properties, click on the parent folder, copy it, paste it in the directory. The output data file can be the same. You can change it if you want. You can put a boost if you want, just to make sure that you know what it is, but that's not really necessary. If you are maintaining your simulations in separate folders, that's good enough. So with this, let's save the simulation parameters. They have been saved, so therefore we are good to go. Now let's go back to the main page, and here let's add the circuit file. So in this, I'm going to choose the circuit file. Here I need to go to the boost converter. It's very important that you choose the right file in the right folder, and here I'm going to choose the boost converter and give it a name, boost converter, save the file, and then now we can process the circuit schematics. And it says the circuit does not have any detectable errors. You can now continue to enter the parameters. So with this, we are good to go, and therefore I will now say that we can now quickly edit some parameters. So let's go back to the main page, go to edit circuit parameters. You see you see our only one and only file, boost converter, view the components, and here you see all the components. So as before, we can quickly edit the parameters. So first we have the ammeter. Let's see what it says. The ammeter is the output, that is a C out. Let's go to C out. This is the ammeter. Now the current through this capacitor flows downwards, so therefore this should point downwards. It is now pointing upwards because the positive direction of current is above the component position. Let's edit this and let's make this 11 ohm. The current through this is component ammeter D1, that is this. The current here will flow towards the right, so therefore the direction should be towards the right of the component, that is 1K. So this is, it is at 1H, it should be towards 1I. It is actually 1G is the other way, so let's change this. Then there is the inductor. The ammeter here is this position. Here again the current flows towards the right. Actually now we have two inductors, so it doesn't, you can delete one, but doesn't matter. So which one is this? It is L1, so it's this one, so it should be upwards. Component position is 1D, no, it's here. This is okay, ammeter L1, component position is L, and it is pointing towards the right. You don't have to change it. Now the other ammeter is here, that is 1A, it should point towards 1B, also points to 1B, so it's the current, this direction also is right, no need to change it. Let me just zoom in a little. Yeah, that's a little better, maybe it's easier to see. Then there is the capacitor. Now the capacitor has to be changed. The capacitor by default is 10 microfarads, so we will have to increase that. Let's increase this to 500 microfarad. Now the positive polarity does not really matter, it's more for debugging purposes, but it has to be upwards, because remember the capacitor here has a positive polarity upwards, so that's good enough for now. We don't have to change it. And let's keep going. After that there is a diode. The diode is at position 1J and the current flows towards the right, which means the diode must allow a current only to flow towards the right, which means the cathode has to point towards the right, which means the component position is at 1J, the cathode should point towards 1K. So let's change that. It is 1J, it is at 1I, this will need to change. And well, JK actually, because it's at point, and therefore this should be the cathode polarity should be towards the right. It can be 1K, 1L, any of them, doesn't matter. We can even make this 1L, doesn't matter. Now the rated voltage, as I always say, should be much larger than what you expect in the system voltage. So let's go for something that's 1000 volts. That's safe. And we can come down. There's the diode, the inductor is 1 millihenry. We can leave it as it is. That's good enough for now. Now the resistor of the capacitor, this is a parasitic resistor. As I said, the reason why we have this resistor is because every branch in the simulation must have some resistance. We cannot have a pure capacitor because the ammeter has zero resistance. So therefore this resistor has to be parasitic, and it's too large. It's 100, or rather this resistance, it is too large. We need something which is parasitic. So let's change this to be around 0.01. And let's keep going. After that there is a resistor. The resistor here is R1. Let's check out what that resistor is. This again is the parasitic resistance of the inductor. It has to be only a very small value. So again let's edit this and make this 0.01. And the load, we can actually change the load. Let's make this a little smaller. Let's make it 5 ohms. The default is 100 ohms. 5 ohms is good enough. And let's keep going. The switch. The switch is one of the most important features. Of course, as before, the rated voltage level should be much higher than what we expect. Let's increase it to 1000 volts. Now, the switch negative polarity, very important here. The negative polarity, as I said, when the switch is turned on, we would want the current to flow in the clockwise direction, which means with respect to the switch, the current flows downwards. That means the negative polarity of the switch is downwards with respect to the component. So which means that the component is at 8F, the negative polarity should be at 9F, and it is the other way around. So we need to change this. Now the control tag. The control tag here can be any unique value. Again, it is more for debugging purposes, not really important, but still I would say always name it to be something which is unique, and the best way to name it is with respect to the component. So I just give it the same name as a component, spelling mistake, S1 switch. That's good enough. So with this we are now ready to save the parameters. And then there should be the last, which is the voltage source. The voltage source, as before, this is a DC voltage. This is a DC converter. So we don't have any AC. So we can just set these to be 0. The DC offset, let's make it a 24 volt or let's make it a 12 volt DC source, which we want to step up to something higher. Alright, that is our objective. Now the component is at position point 8A. So let's go back in here. Look, the component is at position 8A, which means we want the DC voltage positive polarity to be upwards, which means it should be towards 7A, and it is indeed towards 7A, so we don't have to change it. So with this we can save the parameters, and then there's the last one, that is the voltmeter. The voltmeter, again, the rated voltage should be the same as the others because we are choosing a rated voltage much larger, right? It's like the diode here is much larger than the system voltage, which is just 12 or 20 volts, which that's all we would expect. So let's make this also to be 1000 volts. The voltmeter positive polarity, we expect the DC output voltage to have a positive polarity upwards, which means the voltmeter should also measure a voltage with the positive polarity upwards. So therefore, if the component position is at 8S, the positive polarity of the component should be, let's say, 7S. And that's what it is. So we can just save these parameters. So with this, we have completed the parameter editing of our simulation. So I'm going to stop this video now to stop it from going too long. If you have any doubts, please do post in the comments. Otherwise, I will see you in the next lecture, where we will start editing the control for this converter. So thank you so much and see you soon. Goodbye for now.